Hello, welcome to Fundamentals of Acoustics. Today is the last day of this week, and what we plan to do is have some final important points to be discussed in context of DFT so that you can use this DFT technique effectively. So, the first term I am going to talk about, or the first concept which I am going to talk about, is this thing called padding. Okay. So, what is padding? Let us first look at this signal. So, let us look at this signal, and what this signal shows is that you have a square wave, right, or some stepped signal in the system, and in this case we are just measuring 4 points. So, we are measuring at point 1, point 2, point 3 and point 4. Okay. Now, if I do its DFT or discrete Fourier transform, let us say this overall time period is 1 second, overall duration of the. So, in 1 second let us say I am measuring 4 points. So, our sampling frequency is 1 over 4, okay, which means that I cannot, the highest frequency which I can detect in this case will be our sampling, if the sampling frequency is Fs is equal to 1 over 4 hertz, then what do I get? So, F max which I will get will be 1 over 8th. So, that is one thing. The other thing is that I will also lose on frequency resolution. So, what people do is that in the same time signal they put some extra points. So, these are padded points, okay, and so that is what it says. So, this type of padding in the same time period, over the same time period, if I put some padding points, then it improves our sampling frequency and also frequency resolution. So, this is one important concept. And then in the remaining portion of this lecture, what we will discuss is how does duration of the signal affect the goodness of our results. This is one thing. So, I can record a signal for 1 second, 2 second, 3 second, and which of the results will be better, how does it influence. Second thing is how does sampling frequency influence our results, sampling frequency. And the third theme is how do we, what is the relationship between frequency resolution and all these parameters. So, these are 3 important parameters. So, importance of duration of a sample in DFT. So, if the duration is longer, then in general our results become more and more accurate, and we will show that. So, one important criteria is that suppose you have a frequency of time period t, and let us say that is the lowest frequency. So, for an example, you may have a signal which has 100 hertz, 200 hertz, 400 hertz, 700 hertz. So, 100 hertz is the lowest frequency in that signal. Then you should have your duration at least 4 or 5 times more than the time period associated with the lowest signal, because if you do not have a that kind of a time period, your results will be, may not be accurate. So, that is what we are going to show. So, let us consider this signal y is equal to 2 sin 2 pi ft, 2 pi ft, and let us say that initially we just consider this case f is equal to 1 hertz. Okay. So, what is the time period when f is equal to 1 hertz? 1 second. Now, our signal, it will look something like this, right. Okay. and I can either record, I can acquire data up to this much time as one option, I can record data up to only 1/4 of the cycle. So, I can make several recordings and let us see how our results get influenced. So, in the first case, I am just recording 4 points, point 1, point 2, point 3, point 4. The actual signal is going to go like this, but I am only recording these first 4 points, point 1, point 2, point 3 and point 4. In this case, our sampling frequency is 16. Okay. We have set our data acquisition system, we have set that its sampling frequency, see here I have written Fs is 16 hertz. Okay. So, I am going to sample it actually not for 0.3 seconds, to be more accurate it is 0.25 seconds. So, I get 4 points. So, I get point number 1, point number 2, point number 3, point number 4. This corresponds to k is equal to, excuse me, not. So, this is n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, and I will get 4 different frequency components when I do the FFT. Now, theoretically the correct answer should be what is the correct answer? That the amplitude is 2, right? Amplitude is 2, and frequency is 1 hertz. So, F is 1 hertz. Now, this is the FFT plot of the signal. So, let us see what our FFT shows is that we have one peak, one point at 0 hertz and its amplitude is 2. So, this is not right result, and I get another point at 4 hertz and the amplitude is about 0.9 or something like that. Okay. So, we have just taken 1/4 of a cycle and we are getting very bad results, Now, in the second case, I am taking a larger number of points, I am taking 9 points. Our sampling frequency is still 16 hertz. Actual answer is amp is equal to 2, F is equal to 1. So, ideally the correct result should have only 1 point. Now, let us see, I still get a peak at 2, I get a peak at 1.5, I get a peak at 3.5. So, I get absurd results, I am not getting any peak at 2. Okay. Now, consider this, here my duration is t is equal to 1 second, duration of, and this is same as equal to time period. So, I have all the 16 points which help me complete the cycle. The 16th point is this one. Okay. Now, when I do its FFT, so if the cycle is perfectly complete, when I do the FFT, I just get one peak at f is equal to 1 hertz and all other points in my FFT are 0. So, I get a correct result. So, when do I get correct result? If duration of time equals time period. Okay. Now, in this case, this is one cycle, this is one complete cycle and this is maybe 1.5 cycles, right. What do I get? I get a peak at 1.8 at 1 hertz, but I get some other points also. So, this is somewhat accurate. It depends on what is our definition for accuracy, but it is certainly better than this result or this result. It is certainly better than these results. So, the point is that if I have a large number of complete cycles, I start improving my accuracy. This is another case. Here I have 2 complete cycles, I once again get an accurate result. And what I will do is, so this is another case. Okay. So, here I have 36 points, I have 2.3 seconds of data acquisition. So, that is 2.3 cycles, and I see a peak at 1.8 and several other points, but this is the predominant peak. Okay. So, my accuracy is improving as I increase the duration. At t is equal to 4, again it is an integral number of cycles, so I get an accurate result. So, the main theme of this thing is that if we already know what is the frequency, then we can set our duration time same as an integer number of cycles, but usually we do not know, otherwise we would, why would we do the data acquisition system. So, the point is that we have to make a guess that okay, the lowest frequency in my signal may be 5 hertz, its time period is 0.2 seconds, then I should at least acquire my data for 4-5 times that time period. Then I have a good chance that my FFT will be accurate. So, that is the first thing. The second important point to be understood is importance of sampling frequency. So, what is sampling frequency? It equals number of points acquired each second. As per Nyquist criteria, this should be at least 2 times that of frequency of interest. Now, look at this. So, I have constructed a signal which has 6 frequency components f1, f2, f3, f4, f5, f6. f1 is 1 hertz and its amplitude is 1, f2 is 3 hertz, its amplitude is 3, and it keeps on going up to 28 hertz. f6 is 28 hertz and its amplitude is 11 seconds, and I am generating data for 3 seconds. So, that is fairly large, which is good. Okay. Now, f6 is equal to 28 hertz. So, my sampling frequency should be more than how much? It should be, to get good resolution on frequency, it should be more than or at least equal to 56 hertz. If I do the sampling at lesser frequency, I may get somewhat bad results. So, let us look at this. So, this is sampling at 32 hertz. So, I have sampled my data at 32 hertz. So, the best possible, so I will get accurate results up to how many, what frequency? 16 hertz. Okay. At, okay. So, actually I do not get any information below above 16 hertz actually. I will not get any information above 16 hertz. So, up to 16 hertz I get decent information. So, if I compute, so let us look at our numbers. So, I am sampling it for 3 seconds, which is, what is the lowest frequency of interest? 1 hertz. I am sampling it for 3 seconds. So, I have gone up to at least 3 times. Larger is better. Now, so this is the FFT if I do it at 32 hertz. So, what do I get? At 1 hertz, the number should be 1, which is correct. The next frequency component is 3 hertz, which is here, and its amplitude should be 2. So, it is also correct. The next frequency component is 10 hertz, but I am, where is 10 hertz? 10 hertz, and its amplitude is 1.5, which is correct. The next frequency component is 16 hertz, which is here, and its amplitude is, excuse me, 3. So, I am getting some erroneous results here. Okay. I am getting these 2 erroneous results, but if I sample it at 64 hertz, then I get exactly what I want. Okay. So, this point is correct, this point is correct, this point is correct, all these points are correct. So, again, so sampling frequency will help us capture high end frequency component more accurately, and this is data at 128 hertz. So, again the results are identical. So, the last thing is about frequency resolution. Okay. So, when we do a DFT, we get values of xk, right, for n data points. No, not for values of xk for n values, right. So, we get x0, x1, x2 till x to the x n minus 1. So, the question is what is the delta f, that is the difference in frequency corresponding to k equals 1 and k equals 0. Okay. So, what is that? So, that is delta f. So, what is delta f? It is the difference between f k plus 1 minus f k. What is f k plus 1? It is k plus 1. So, we have explained this. This is the actual frequency. Actual frequency is k divided by n times fs. So, it is k plus 1 minus k divided by n times fs, and so that is equal to fs over n. So, delta f equals fs divided by n equals 1 by time period. Okay. 1 by time period. So, what does that mean? If I increase my n, if I increase, so this I am sorry, this t is not time period, it is the duration of data acquisition. Duration of data acquisition. Okay. So, what does this mean? What it means is that if I increase my time period or the number of points, then this distance delta f, it will become narrow. So, I will get more frequency. So, there may be some frequency which I may miss out if n is small, but if I want to capture that particular frequency, I have to narrow this delta f, and I can narrow it by doing what? By increasing the number of points, which essentially means that the duration of our data acquisition system, duration of data acquisition has to be long. Okay. So, if duration is 1 second exactly, then what will be the delta f? Yeah. So, if duration equals 1 second, then delta f frequency resolution will be sampling frequency fs, and how many number of points I will get? Fs, hai na? So, that is 1. So, if I acquire data for 1 second long, then I will get frequency resolution of 1 hertz. So, I will get one data point at 0 hertz, 1 hertz, 2 hertz, 3 hertz, 4 hertz, and so on and so forth. And what is the maximum frequency I will go up in this situation? It will be fs divided by 2. Okay. If I increase my duration to 2 seconds, then I will go up in steps of half hertz, 0 hertz, half hertz, 2 hertz, 1 hertz, 1.52 and so on. And the maximum frequency which I will go up will be, it will still be fs divided by 2. So, I cannot exceed the maximum frequency beyond fs over 2, that is the mathematical limit, but I can go in finer steps if I increase my time duration. So, this completes our discussion on DFT, and then there is one last point, that just as we had forward and inverse transforms in continuous functions, this is the expression which will help us convert time domain data, discrete data. This is the expression which will help us convert time domain discrete data into frequency domain, and if I want to convert frequency domain data, discretized data into the time domain, then I use this relation. then I use this relation. Okay. So, this is the inverse of fast Fourier transform. So, with this we conclude our discussion on Fourier transforms and DFT, and next week onwards we will go into another application area which will help you use whatever knowledge you are gaining in this course to your actual field problems. Thank you and have a great day. Bye.